I really struggled preparing that talk. I was actually preparing it this morning still because of that. Because I mean, I've been around some of us here for almost a month now, and I talked to so many about so many aspects of this, so I didn't want to be repetitive. So I hope I managed to strike the right balance to try and tell people who don't know everything my group's been doing for the past few years and tell you a bit more, and then also go deeper into some of the details. So let's start by talking about weirdos in astronomy, and specifically, we're generating, and I'm talking here from an observer's perspective, we're generating, I don't want to say too much data, but a lot of data. With so much data, we can no longer look at everything by eye. We can no longer say, oh, here's something we've never seen before. But that's how we discovered quasars, and that's how we discovered pulsars, and many things were discovered because somebody looked and said, oh, that's something we've never seen before. So this is something we need to be aware of and think about, but there's another reason, and that not everything we find is quasars, a new type of source. That doesn't happen very often. But even within a known class, looking at outliers is a way of finding what physics can do, what your model can do or cannot do. So outliers really stretch our understanding of the types of objects we're looking at. And also, small, okay. The second thing is that actually you could say that pretty much everything in astrophysics is an outlier. The universe is really empty. So stars, galaxies, supernovae, all of those things are rare from a pure data perspective. I'm not saying that to be silly. I'm saying if you can pose your problem as an anomaly detection problem, then you can use those tools. So this is why this connection is actually useful. And I'll show a few examples of that. Also, this is specific to astronomy. Something that is rare observationally can actually be very common, but short-lived. Supernovae, again, is a good example. So again, anomalies are important, and this point is obviously especially true for galaxies. There's another reason you should care about outliers, especially if you're running or planning a survey, and that is that when you generate a lot of data, you have a lot of problems. Just to give an example, so this is 1/10 of the focal plane of DESI being built. All of these are of robotic fibers. There are 5,000 total on the camera, or will be. I don't know if they reached the full focal plane. They did. So that's about 50,000 spectra every night. I mean, in the morning, you need to figure out whether you have 50,000 spectra that are fine, and how do you know if there are 500 that are not? This is not an easy question. This is not something you can do easily. So you need some tools that will help you aggregate that information. And of course, this is just an example, because you have Sloan 5 and Subaru PFS and Foremost and other surveys that are coming online already. It doesn't help that anomalies are a very ill-defined thing. Typically, when we think about anomalies, we think about those things. These point anomalies or group anomalies. We have a group of things that are anomalous. These low-level texture anomalies, actually, Lina's streams kind of reminded me of that, in this sort of small perturbation in the density that are harder to find, or you have to find through that definition. In terms of light curve, you can have an anomaly where a point is anomalous, but you can have a whole light curve that doesn't look like all the others. And this is, I should say, from a review in computer science, these are what they call high-level semantic anomalies. Obviously, the anomaly here is not the dog, it's the cat, because he's grumpy, and all the others seem pretty happy. But this is as good as definition as the others, right? I define what it is I'm looking for when I'm looking for anomalies. And so there are many possibilities, and they will find different things. And if you change the parameters, you'll find different things. It's ambiguous by construction. It can be frustrating sometimes, but also fun. And just to give an example of that, here you see a clustering problem. I should put problem in quotes, but you can group those circles and squares of different colors and sizes in 6 different ways, and they're all defendable. You can cluster them by size, by shape, by some kind of combination, and you can argue for either, and if you can cluster them differently, you can find them differently. So how to find things, how to find anomalies. I'm going to sort of take you on a journey of the things we've been doing. And I'll start by how not to define similarity when we talk about spectra. And this is a problem. Calculating spectra from a theoretical perspective is a difficult thing. And so when you find the first kilonova, the first electromagnetic counterpart to the first neutron star merger, you feed models, and then you say, look at my models in red, and look at the observations in black, and they fit. But they don't. Now, let me start by saying this is an amazing achievement in many, many ways. I'm going to go back actually to the gravitational wave detections, but even the spectroscopic fit, if I can call it that, is impressive when you think about the fact that it's the first time we ever see something like that. And it's a new type of transient. We've never seen it. The light curve is different from everything we've seen. The spectrum is different from everything we've seen. And if you squint, the models kind of have the right shape, which is the best we could do and can be done at the time. But the lines are not there, and it could be spectroscopic observation of our process. If you want to say that, you know, without our process elements, it's difficult to explain the light curves and the luminosity, therefore you have light, and it's spectroscopic observation, so there you go. But there's no identification. There's no line here you can actually fit and say, I've seen gold or I've seen any other result of our process. So fitting spectra is difficult. How do you still do it? You can't do it with chi-square. If you define your spectrum as this sort of just f of lambda, and your dimensionality is just a number of wavelengths, just again, like in Lina's talk, which she had apogee spectra with a few 7,000 or something wavelength. If you define the distance between objects as the sum of flux differences, you won't get any meaningful results. Most of the wavelengths are repetitive. This one will do what the next one will do, pretty much what the next one will do, unless you hit a line, and then the next few lines will be correlated, the next few wavelengths will be correlated because they're sitting on the same line. And that line will correlate with another line. And if you're in the continuum, there's a lot less information. So there's both a big variance in information content, and also, this is something I will go back to, Euclidean distances in large dimensionality are not very useful. So that doesn't work. What we found that does work is using unsupervised random forest. Now, this is a prehistoric technique. This is already from 2001. But actually, the idea was in the original Breiman paper on random forest. I think it's a fair assumption that you all know what random forest is, but I'm still going to say it in 2 sentences. You take the data, you break it into smaller pieces, and you take those smaller pieces of your data, smaller views on not all features, and you train trees to classify that subset. And you have a lot of those trees, a lot of weak classifiers. They all give you an answer about your question, whether it's classification or regression, and then you can aggregate. And it tends to average out all sorts of problems and give pretty robust results. With unsupervised random forest, what you do is you create a synthetic data set. I won't go into the details now, but if you want to ask me about this later, no problem. And you train a random forest to separate the synthetic data set from the real. And when you do that, you're effectively teaching your algorithm what a normal, in this case, galaxy spectrum, I will show you what a normal galaxy spectrum looks like. And once you have that, you can throw away the synthetic data. And you can ask about every 2 objects in your sample, whenever I pass them through the same tree, do they land in the same leaf in the end? Because if they're identical, in every tree, they will always land in the same leaf. And if they're completely different, in every tree, they will go their different ways. And so I have this sort of, I span the whole difference in between things that are completely identical, completely different, and then I have this pairwise similarity measure. Once you have that, you can look at outliers as the objects that are least similar to all the others or other definitions. So we started doing that back in 2017, and we essentially sorted all the galaxy spectra in Sloan. At the time, I think there were about 2 million. And we looked at the 400 the most outlying or the weirdest. This is sort of the cutoff there. The weirdest was nice to me because I'm kind of filled with supernovas, but the one at the top, which doesn't mean a lot, still fun, was the host of a supernova. It makes sense. Supernovae have very broad lines. They change significantly the shape of a spectrum, so it's not super surprising. We found stars. This is an AMCBN. It's a rare type of stars, but it was in the Sloan catalog as a galaxy. We found some, you were asking me, so I put that slide just for you. Some chance alignments and galaxy lenses. You can see here that, all the lines are two systems. Actually, many of the things we found here were BPT outliers, so objects that don't have the line ratios you would expect for galaxies. I'm going through these quickly because I have more recent things to show you. The first surprise was that we actually were sensitive to very different kinds of outliers. In addition to everything that I just showed you that we found outliers I would call big, where there are just a lot of dust, and so the spectrum is very, very red. I'm not a galaxy person. I've seen spectra of galaxies before. That was the first time I saw something like that. So it's really not something you see very often, but there's a bunch of those in SDSS. This one looks kind of fine. Not a big deal until you zoom in on the sodium absorption, and you see that it's insane. Again, people looking for those kinds of things have found them. There are a bunch of them known, but this is an algorithm that knew nothing about galaxies and just picked the things that were outlying in a general sense, just from the most outlying to the next, and we found very, very different types of outliers. The second surprise to me was that we actually found something new. Not obvious when the Sloan spectra have been around for 15 years, and it's only, and if you look at the high resolutions, the high signal to noise ones are only a few hundred thousands. They've been looked at by many people. And yet, here is a very weird object. The redshift from SDSS was completely wrong. It tried to fit this double 002 line as H alpha, and that didn't work. You see that all the lines here are doubled, like perfectly doubled, with a 700 kilometers per second difference, which is a lot. And I can tell you because we got some very bad IFU data with KCWI when it was commissioning, but we resolved the two components. So there's something going on here. I don't know what's going on yet. We don't have good enough data to explain what's going on, but this is truly a 1 in a million object, because literally we looked for it, and then we use our metric to say, can we find more of this one? Because now I have a similarity measure. So I can just look for things that look like this, which we did in another paper. And we didn't. So this is really the only one we found. Of these guys, we found a couple more, but not more than a couple more. So this is, again, also something that is very rare in Sloan. This emission line at 5,200 angstroms that you don't see in galaxies. Well, you see once in a million. But this is a very inefficient way of looking at a million spectra, just going from the top of the list, going down. Many things are repetitive. We've seen this one. This one looks exactly like the other one. So dimensionality reduction can help you a lot in there. So here we start with apogee spectra, so near-infrared spectra of stars. Tons of information. You were asking about the resolution we saw earlier. This is a spectrum from apogee. They're insane. All that. There are two lines here. It's difficult to see, but there's a red line, that's the model. The black line is the observed. You can see a zoom in here of the part. It's about 10,000 features, I guess 7,000 something. About 200,000 spectra. Using, again, the unsupervised random forest, we reduce that dimensionality and we find similarities. But then we also use TSNE, which is an algorithm for dimensionality reduction that maps all these objects to a two-dimensional space that is where the axes don't have any significance, so I can't tell you what the x or y axis mean, but every point here, it's so small it's difficult to see points. There are about 200,000 points in these two plots. Every point is a spectrum of a star, and similar stars are close to each other. So spectrally similar ends up being close on that map. You take that map, and then you can color it with the metadata we get from the model fitting, the red curve here. And when we do that, we see that we can actually, this mapping makes sense. You can see that red and blue stars are not in the same place. Low metallicity stars tend to cluster in some other area. So you can use that to study your data and also find your outliers in a more efficient way, because now you can pick them in different areas of that plot with different properties and see, for example, things are, oh, really? Oh, that's right. So we're working on various domains. One of the thoughts we had and we started working on is working on gravitational waves. Two detectors in LIGO, detecting very small changes in the gravitational field, enough to find these mergers. They find them by match filtering, because when you know what you're looking for, this is the best way to do it. But can we do better with machine learning? Given the time, a good reason not to do it is that many people are doing machine learning on gravitational waves, but we're the only ones who are doing what we're trying to do now. And I skipped to this because, again, the question is, how do I find things as outliers? Here I have, in every week of LIGO, there's perhaps one event. So what I have is a lot of background. So the way I find sources, the way I define the problem here, is I define real astrophysical sources as outliers to the background noise. So I teach a network to understand the background noise of the detectors. I use the fact that I have two, so I teach it, I trick it by asking it. Earlier I did it with random forest, asking it to separate real galaxies from fake galaxies. Now I'm doing it, can you tell me whether a spectrogram is coming from Hanford or Livingstone? And if you can separate, then in the process you've learned what the background noise looks like. And if you can do that, then you can look in some latent space, like we did before, and expect them to cluster in separate areas, because that's what the network is learning to do. And an astrophysical signal would be an outlier in both of them at the same time, so a coincident outlier. That's the ideal. It actually works. Our current best model that we realized as of yesterday that we know how to fix, thank you, was trained with about 10 to the 6 samples. We're using visual transformers. We get an accuracy of about 97% in this fake task of separating the two detectors, which is good enough to do what you want to do. The latent space has 32 dimensions. If I send it to 2 dimensions, you see this. So this is one of the detectors, the other, and you see this long bridge connecting them with a lot of stuff that looks like a lot more than 3%, which shows you that 2 dimensions are not enough. It's nice to have 2 dimensions. You want to do that, but you can't. You can't always. Sometimes you need more than 2, and that's an example of that. Now, in the 2 minutes I have left, let's see how much I can say about the recipe, which is what I tried to hide. So we talked about this. You want to map the data to a latent space. You want it to be low D enough, interpretable, and then you can look for outliers. I'll get to the main point. This I already mentioned, so I'll do it quickly and just say that 2D is nice for visualization, but often not sufficient. Still, you want a small enough dimensionality so that you can more easily interpret what you have. It's difficult to find your feet and your hands when you have 15,000 dimensions. Another point is about the interpretability of the space. You don't always have this sort of eigendecomposition where the axes actually have a true meaning, but by using the metadata and everything you have, you can make that space interpretable, understand where the different kinds of object cluster. As I showed, this is what I mean by interpretable in this context, so how different objects cluster and go together. To find outliers in the latent space, you can define them as objects where the density is low. Density is difficult to measure in a space where you're sampling and you're going to make a bunch of assumptions depending on the method you use, and so you'll get different results. So this is something to be aware of. Distances are easier in that respect. I guess I will mostly stop here and say that the problem is that the difficulty with these kinds of things is that we don't know when to stop. There's no clear view of when you know you've done a good job, because the proof is in the pudding. So you search for things until you find something, and when you find something, you're happy. And if you haven't, well, perhaps search in a different way. So this is not an easy thing to do very often. And the low-hanging fruit were already picked with traditional methods. As I said, people look at data. Not for long. They'll have to stop at some point, but they still do it. And you need really this combination of subfield observation, understanding the subfield, the observation, and the methods, which is why you can at least separate some of that by incorporating a lot of tools into whatever pipeline, whatever project, whatever everything. I know I'm good. I'm just saying, put those things in online tools, give those tools to people who are experts in their field, and let them use them. That's it. Thank you.
Thank you so much, Dovi. Does anyone have any questions for Dovi? Please state your name before your question.
It's working.
Okay, so I guess I really like the outlier detection. Like, you've completely convinced me you can do a good job on all these different domains. But I guess like the thing I struggle with is kind of, then what? So to take your like apogee example, you have these really nice TISNI maps, and you show that, like, you know, different metallicity stars have different looking spectra.
Yeah, so it's a very good question, and here I again will misquote probably David Hogg, who said when we talked about TISNI many years ago, and he said, the first thing that happens when you run TISNI on your data, you get this beautiful plot, and then you say, oh, I've got to write a paper, and then you realize you don't have anything to write. Because it's nice, it's pretty, but it's not the science. It's just a way to get there. And that's true about all of those things. So in the galaxies, I showed you what kind of things we find, and if you care about galaxies, you take those objects, you follow them up, you study them, and that became Dalia's PhD. There are things we found there that she took into a completely different directions, and that what you do with those things. In the apogee stars, there weren't many super exciting things. We found a few outlying stars. We looked at them. There was nothing super exciting. The second point, I guess I will add to that, when I say experts, it's not just putting it online, but also collaborating. And so the result will also depend a lot on the people you have in the collaboration that know the field and can take it into different directions. And so I'm trying in every one of those projects to have someone from the field who knows the burning questions, can find the interesting things, because I'm learning, but I'm new to many of those fields. So.
Thanks, Dovi. I was wondering if you found any new gravitational wave signal with your method, or everything was known?
No, not yet. I really think we have a very sensitive detector, but at this stage, it's my gut feeling. I don't actually have the results to support it. It's just I see the process, I see how it's going, I see what. Yeah, you've been there before. I know it's gonna. It feels like it's gonna be good, but I don't have results yet. We're just training right now on 01. So that's the first observing season when they actually detected something. So there are 3 black hole mergers that we need to recover and see what else we can find. This also goes back to Toby's question. We're not just looking for new types of sources, which I think we should do, because if we don't look, then how do we know if there was something? But we're also learning about the noise. So when I talk to LIGO people about what I'm doing here, they wanted this, and they wanted to hear more, and they wanted to do more, because that's a way of figuring out what happens in the detectors and what does the noise correlate with, because you can find those things if you have a very sensitive detector that really understands the noise, then you can map how it correlates with other tracers and things.
Hi, sorry, John Wu. So yeah, thanks for this. I'm curious about when you were talking about, for example, using a random forest to extract, look for these, sorry, to look for these outliers, or using like a vision transformer to look at visual or outliers in the gravitational wave signals. One of the questions that I think about is, like, how are you coming up with a physical, a set of latent features or whatever that allows you to really look for outliers in some sort of physics-informed way? Or in other words, I mean, if you think of a random forest or a decision tree as just a bunch of nested if-else statements, that doesn't really capture the inductive bias that you might expect, in looking at like a galaxy spectrum. And similarly, if you look at a spectrogram and then you use a vision transformer, I mean, you're kind of patching up, the spectrogram, and you can find like local features, but maybe you expect that outliers are connected along, you know, the entire spectrum in some non-local way. And so I'm curious.
So I think your question makes 2 points, which are both correct and non-trivial, which is how do you get from whatever data space you're in to something that informs you about the physics? That's one question. And the other, if you're sensitive to things that are local in whatever data space, you're not necessarily sensitive to things that are more global. And so when you search in one way, you won't be sensitive to things that you might have found in another way, which is true. But that was sort of my point in some way. You can't do everything at once, and the decisions you make will take you into some directions. In terms of informing the physics, this is harder, but that's always hard when you start from a purely data-driven thing. I don't think there's a good way, at least not that I'm aware of, to do it within the method. But you know, once you've done it, you're a physicist. You take the data and you try to understand it. I think that's. Got
it. Thanks.
Risa Wexler, nice, really cool stuff, and lots of ways to explore the data. So this thing about the gravitational waves is an interesting example of where you might basically be building a more sensitive detector. Do you have examples from the Sloan work where your weirdness identified something, even if it was a known object before, and then somehow your techniques allowed you to push farther into the signal to noise to identify more of those kinds of objects?
Okay, so yes and no. Once you've found something so in Sloan, out of the 400 that we looked at, about half, if I remember correctly, were already known. Now, in terms of benchmark, we're finding things that people have looked for and searched for as weird, so that worked. But for any specific class of those, we're not as good as them. Because when you build a class, a system, just a query actually, that gives you all the objects that have very strong sodium lines, you'll find all the objects with strong sodium lines. By the way, I mean, there are problems, because you go to the extremes of the fitting and you find all the junk too. So not so much in that respect, but yes, we have an example where there's this class of quasars that have redshifted broad absorption lines. There were 17 knowns, because somebody went over a few 100,000 SDSS spectra and found those 17. We took those 17 and we asked which of all the other quasars are most similar to those. Took a few hundred. Itamar, my student, looked at them, and we tripled the known sample. So this was a very easy exercise. Once you know what it is you're looking for similarities useful. It's harder to get to completeness and those kinds of things, so it's a weird kind of way of searching.
Hello, Chingwen. Really great talk. Have you think about applying your detection method to LIGO time series data? And also, LIGO has usually a lot of transient noises or glitches. How does in the latent space, where does the glitches live, comparing to an astrophysical signal?
Here, these are the glitches. So let me explain. So we are classifying and working on the strain. Only we're representing it as spectrograms, as images, and not on the time series. We can talk about this offline, why I'm doing this way. I don't like it too much, but that's what we're doing. The first time we worked on gravitational waves, we actually used these very weird nonlinear noise transient signals in LIGO as our training set, because it was a labeled set. So there's so few labeled sets in astrophysics that we immediately went and used it. And so in this work, what we did was define the sources we were looking for as outliers to that glitch, the glitch families. There are various groups. They have all sorts of weird spectrograms. And when you cluster them with, I think, UMAP here, they really cluster very well. And so a source that is not a glitch would be outside these groups. That was basically the idea. It worked, but it was very insensitive, and the reason is that the glitches are very loud. They're very bright sources, And so when you train on very bright sources, it's difficult to really be sensitive to faint things, which is why we switched to using the background noise. Glitches, we'll just find the glitches, but they won't be coincident and they will be different. We find them. I don't think they're a problem.
All right, let's thank Dovi again.
Thank you.